Hello everyone, this is Mark Anderson, Director of Conservation Science for the Nature Conservancy's Eastern Region, and I'm here with Arlene Olivero Sheldon, landscape ecologist with the Eastern Region. We're to talk about our lake and pond classification and GIS map for the Northeast and Mid-Atlantic states, which is a big project funded by the North Atlantic Landscape Conservation Cooperative and the Nature Conservancy. So in a short introduction, we'll go over the goals of the project and the process of classification, collected the data and came up with the key variables and modeled them for the region, and how we integrated that into lake types and the interpretive materials that we put together. The goal really was to really understand the water bodies in the region through classifying and mapping ecologically distinct water body types. There's 30,000 water bodies in this region, quite a few. And this classification is intended to link together in classifications that have been put forth by some of the states or academic areas to sort of bring them all into one system that works across states. But it's not intended to override those more local classifications. Classification of lakes and ponds is a complement or a counterpart to the Northeast Stream Habitat Classification and Guide that we completed a few years back that classifies and maps all different types of streams in the region. So with this, we'll only have the streams, lakes, and ponds all put together. The project took over just to do, and we had a large steering committee of representatives of agency biologists from all the different states involved in the region, including also some federal biologists who helped a lot with coming up with getting us the proper data and coming up with a framework. So the steering committee, we met and talked with them about every other month and tested approaches with them, and they were really critical in guiding the development of the classification and the final products. One thing we really wanted to do was focus on compiling as much field sample data as we could. So you see there's a lot of modeling involved in the final products, but to our best ability, we wanted to gather real data. So we got sample data from most of the states on temperature and dissolved oxygen, alkalinity, chloral A, depth, water body depth, and many other parameters for 3,000 water bodies, and they constitute the bulk of the sample from which the models are built. We put a special emphasis on lake depth, which is, as you see, a very important variable to systems, and many have done a pretty good job getting this information from their water bodies. So, almost 6,000 water bodies we knew the actual depth. For those we didn't, we had some good modeled depth estimates from Lister's paper. And to the attributes that we collected for each water body, we also collected a lot of attributes about the context of the water body, the water that it fell in, or the buffer area right around it. And we ended up with about 315 of these descriptors that are in the GIS data set that goes with this product and give you information on dams and soils, landforms, geology that the lake falls in. But we focused with the steering committee on 4 key classification variables that there was unanimous agreement on were really the variables that structured the lake system and determined the biota to a large extent, and were temperature, trophic state, depth, alkalinity. And it was for each variable, we worked at those one at a time. We really clarified what was the ecological relevance, and you'll hear about this in a minute. And then we defined the classes, for instance, temperature classes, what temperature classes that correspond with observable biological changes. So you really get a change in the species that are using this lake. We then collected sample data on that particular variable and modeled the variable for the unsampled water bodies. Using a statistical pattern called random forest, which does a great job of predicting classified variables based on the landscape attributes we provided it and the sample data where we knew what the correct the variable was. Now to Arlene Olivero, who did the bulk of this work to get through the variables in depth.
Okay, hi. So I'm going to start with our temperature classes. So the group developed 4 key temperature classes, ranging from very cold, where we have fish like lake trout, through cold, where we find wild brook trout reproduction, to cool water systems, with species like northern pike or white sucker or yellow perch, and then our warmest class, where we only have warm water fish, largemouth bass, species of sunfish, chain pickerel, brown bullhead, and species like these. And so the team really felt that it was important that we map and try to distinguish at least these 4 major temperature groups within the water bodies. Again, as Mark said, by collecting known field sample data. So temperature, we use July or August temperature and dissolved oxygen profile data, and some fish reproduction data for a few water bodies where we didn't have the temperature dissolved oxygen profiles. And we classified each lake or pond into one of these 4 classes based on the coldest temperature dissolved oxygen category that was found in the water body. So you remember from the previous slide, 4 classes, and they were divided by temperature and dissolved oxygen. So very cold category, you had to have more than just water below 0.8 degrees Celsius. You had to have also very high oxygen. So the temperatures present in the water body, classified each water body based on the cold temperature dissolved oxygen class water body as the most limiting factor. So to model water bodies where we didn't have the known temperature dissolved oxygen profile data, we built a random forest model, and it's a 2-part model. So the first model separated the very cold, and the cool warm waters from each other, and the secondary model separated the cool from the warm. Model, you can see from the chart on the left, maximum depth by January mean temperature and April mean temperature as the key variables, along with a few others we see in the graph. And those were used in the cool versus warm model. Again, maximum depth being the variable that explains far the most of the in the model. And for the cool versus warm model, minimum temperature and percent of watershed that was forested were also variables which were used quite highly by the model. Applying the model to all of the data points, we were able to map out the 3 classes or the 4 classes of temperature through the region, as you see in these maps. So to go through the trophic class variable, for this variable we collect July or August chlorophyll A data. There's a number of different ways to measure trophic class, and the team agreed that chlorophyll A was a reliable and a good measure that we could apply across the whole region. So we did chlorophyll A data from samples, water bodies, and placed the water bodies into one of four classes based on EPA thresholds in chlorophyll A that are used across the nation. Separated our water bodies again into oligotrophic for our very low productivity, nutrient poor water bodies, a mesophytic class for a more moderate productive system, eutrophic system that we're beginning highly productive and nutrient-rich systems with murky water, through our hypereutrophic systems that had excessive nutrients and productivity. When we ran this data through random forest, we were able to create a model that separated the oligotrophic, mesotrophic, kind of low to moderate productivity water bodies from the eutrophic, hypereutrophic, high to very high productivity bodies with a accepted error rate of 23.6%. We could not separate these classes further, although we tried a number of things. We just could not, with our landscape variables, create our class trophic model. So ultimately, on using this two-class model, which gets at the major in between the activity levels within our I just put a slide showing you here the confidence data that's also available for every water body in every one of our models in the distributed data pack. If you're interested for each water body, you can click on it and find out what confidence the model was able to predict for that particular water body, its class. In this case, the trophic, which you see here, shows you that 6% of our water bodies were classified with high confidence, 6% were classified with lower confidence based on the probabilities of our model. But we felt good about our final classification, which you see here in this map. So, we based our depth classification on threshold light penetration, which is also dependent on the trophic state of the water body. So we're looking to section ponds based on the distinction between where light does not penny further and where there'd be no photosynthesis. So ponds have light penetration throughout them and photosynthesis throughout them, and the lakes have them where there's no photosynthesis or light penetration. So we use a depth threshold of 10 or 20 for lakes on the trophic class, as trophic systems had more water and further light penetration, and then on the depth had less than 10 or 20 foot threshold. In fact, most of our water bodies in the region, almost 80% of them, are ponds. The lake population, which was much smaller, about 21% of the data set. For alkalinity, we separated our input data into classes, high, medium, and low. And again, we collected field sampled alkalinity data as a measure of brain capacity of the water bodies to look how they are from acidification, and this is related with the pH of the water, which influences the biota. In our alkalinity model, we were able to build a model with the landscape data that had error rate of 20.9%, and again is based on a few variables that came out of the random analysis related to the percent of calcareous bedrock in the watershed or the water buffer of the lake, in addition to a few other geography variables and percentile within the buffer of the lake. Also, watershed soil erodibility, which is, we think, related to kind of a proxy signature for calcareous materials, since calcareous soils are more erodible. And so our result map shows areas of high, medium, and low alkalinity. And 70 water bodies were classified with high confidence in this model. So we felt map recall this particular attribute of the lakes and ponds. Combined variables, we discussed with the team we should collapse or combine the different variables, and we settled on a final assessment of major type for each water body based on a temperature class, trophic class, and alkalinity class. And temperature, we ended up using only 3 of the 4 temperature classes. People felt that lumping to cool water bodies would be appropriate in our region. And we wanted to keep the very cold and the cold distinct from each other. And then combine that with the 2 trophic classes and the 3 alkalinity classes, the 2 depth classes, to come up with our types. So the common type in the region is a warm to cool eutrophic circumneutral pond. And in the report, you can find tables of how common or how many of these types of this occur in the region, and you can find the map of the resultant where you can see the very cold type blue in the more northern, higher elevation areas, and the warmer types in red. And if you really explore the results, we've created habitat guides and an interactive story map, which I'll quickly show you. So the habitat guide, a 2-page summary for each of the 18 major types. It gives you the name of the habitat, a distribution map of that particular habitat, a description of how served the land around the riparian area, around the water bodies are. So you can see the distribution by state and observation of the riparian area. You get a photo of the habitat and a little text description along summary of the water bodies and the criteria that was used to define this type, and also some places that you can visit that are publicly accessible. A second of each habitat guide report, we cite a list of associated species. Start with some commonly associated fish species, and then also provide some of the information of rare species, species of concern that occur as habitat. There's a little temperature depth profile graph along with another picture, and then summary charts on the condition of this habitat. So again, how secured is the riparian area of this particular habitat type across the region, information on the land cover classes within the riparian cover area, the dams on this particular type of habitat, how dammed are water bodies, and on impervious surface characteristics of the watersheds that drain into these water types. And we have an interactive story map where you can go to explore the data, and we invite everyone to view a place that you know and check out the types of water bodies in your area, you can click on the story map and it will bring you to pages that give you a little bit of information about the classification variables, and then you can zoom in and click on individual water bodies. You can scroll through available attributes that tell you the water body, the size of it, the depth of it, and then what classification type it was assigned to in our classification. So we want to encourage you to download the report and the data and explore the web map by going to our website. Again, thank everyone who participated in this project.